All right, for our next talk, it'll be about libLISA, and Jos is giving the talk.
Thank you. So, when we have a program that's been compiled to a binary, all that we have is a bunch of bytes. And we might still want to know what these bytes do, what the program does. And if we don't have the source code, maybe because this is legacy software, or maybe because this is malware and we simply don't have access to the source code, then we have to analyze these bytes. And so this is still a very vague question, what do these bytes do? So to make that a little more specific, from my point of view, a CPU is a machine that repeatedly updates CPU state. And it does this by fetching an instruction, which is just a sequence of bytes, and then according to this instruction, it performs some kind of modification to the CPU state. And so the more precise question to ask is, how do these bytes actually modify the CPU state when we execute them? And so that's essentially what CPU instruction semantics are. They take bytes or instruction as input, and they produce some kind of description of how the CPU state is updated as output. And of course, ideally, we would like that to be in a format like this, which is nice and formal and machine readable. But that's not what we get in practice on x86 CPUs. What we get is a 5,000-page PDF with natural language descriptions of each and every instruction. So if I want to write an analysis tool that analyzes binary, I need to manually translate all of these 5,000 pages to something that my analysis tool can use. And to make matters even worse, when I have done that, as it turns out, these manuals are actually not that accurate. Basically, every time someone takes a look at them, they find inconsistencies, errors, and discrepancies. So now I have spent a lot of time writing down these semantics, and now they're not even correct. So when I first ran into this issue, my thought was, well, we should automate this. We should take the human out of the loop and do this all automatically. And that is essentially what libLISA is. It's a tool that takes CPU as input and automatically analyzes it and produces CPU semantics as output. And it only needs two things for that. It needs a description of what the CPU state is, so which registers are there, which flags, etc. And it needs a way to observe execution of an instruction. So it needs to, given a certain CPU state and an instruction, it needs to be able to check what the modified CPU state is after executing that instruction. And from that, it can automatically infer the semantics of all instructions on the CPU. And so how do we do this? Well, a straightforward approach might be to simply start enumerating every possible bit string. And then we can check with the CPU observer if that bit string is actually a valid instruction. If it is, we yield it, and that gives us a list of all instructions on the CPU. And then we just need to infer semantics for every instruction. And this might work for a smaller CPU architecture like RISC-V or maybe ARM, where the amount of bit strings that you might need to enumerate is limited. But this doesn't work for x86, for the simple reason that on x86 we have instructions like this. And this is only 40 bits. You can easily have an 80-bit instruction or even longer. We're not going to be able to enumerate 80 bits of instructions. So we need to find a different way to actually enumerate all instructions on the CPU. And one of the ways to do that is to realize that this instruction is actually not that unique. There aren't billions of different instructions on the CPU that all do unique things. For example, this instruction, the last 32 bits are actually just an operand, an immediate value that is used to update the CPU state. And the 3 bits before that are just a register operand that is used to write the result of the computation that this instruction does. So what we can then do is we can start inferring the way these operands are encoded into the instruction. And we can replace this immediate value with a part that says, well, here is a 32-bit immediate value. And this operand, well, it can be a part that indicates that here is the destination operand of this instruction. And now we have an encoding that describes 32 billion different instructions that only differ by operands. And that is what is going to allow us to actually enumerate all instructions on the CPU. Because what we can do is we can, when we've done our enumeration and we have a bit string, we can immediately start analyzing the encoding of this bit string. And that gives us a group of many instructions that all only differ by operands. We can then use this encoding to speed up enumeration. So we can skip all of these 32 billion instructions that do the same thing modulo its operands. And that makes it feasible to actually enumerate large instruction spaces like x86. And then all that's left after that is to run some standard program synthesis to synthesize the semantics for each instruction that we found. And so that is how libLISA works. Now, of course, if we run this on an actual CPU, we might get different results on different CPUs. And in fact, it's very likely that we get these because x86 has some undefined behavior in its instructions. And what that really means is that these instructions are doing something that's implementation defined. So every CPU implementation can pick its own way of executing this instruction. And that means it's actually very likely that we'll find differences among different CPUs. And so that's the reason why we've actually analyzed 5 different CPUs. So we've run libLISA on 5 different CPUs, on 2 AMD CPUs and 3 Intel CPUs. And it takes roughly 7 to 21 weeks to run this analysis. And that gives us 120,000 different encodings, so 120,000 different groups of instructions that only differ by operands. And one of the interesting things is that we found a bunch of undocumented encodings on AMD CPUs. And so these instructions are essentially copies of the vperm_q instruction. And they exist because these instructions need a very specific bit in the instruction bit string to be set for them to be valid instructions. And AMD forgot to check whether this bit was set or not. So all the instructions where this bit isn't set also turned out to be the vperm_q instructions on these CPUs, while they shouldn't be. And finally, we are also able to, as it turns out, synthesize this undefined behavior that some instructions have quite well. So for around 90% of all encodings that have undefined behavior, we're able to synthesize their semantics. So that means that we can also compare these differences. And when we do that, we get a table that looks something like this. So here at the top are again the 5 architectures that we analyzed. And then each group is a group of instructions that has the same kind of differences between its implementations. So for example, group 0 is the group where all implementations do exactly the same thing. So these instructions are all equivalent. But group 1 is a group where there are actually 3 different CPU implementations. So architecture 0 and 1 share an implementation, architecture 2 and 4 share an implementation, and architecture 3 has another implementation of these instructions. And when a symbol is missing in one of the rows, that simply means that this instruction is not supported on the CPU. That can be, for example, when you have CPU instruction set extensions like the SHA-256 instructions that are not actually supported on all CPUs that we analyzed. And one of the interesting things that we can do with this table is that we can use it to identify instructions that we can use to fingerprint the CPU that we're running on. So for example, if we take one instruction from group 1 and one instruction from group 7, and we observe how they behave, what their implementation is, that's enough to actually identify which of the 5 CPUs we are running on. For example, if we check the instruction from group 1 and its implementation turns out to be the red circle implementation, and we check the instruction from group 7 and it's a blue square implementation, well then we must be running on architecture 2, because that's the only architecture that has this specific combination of implementations. So now we have, of course, a lot of semantics, and we might also want to make sure that they are actually correct. So to do that, we picked the formal semantics by Dasgupta et al., who manually implemented most of the instruction set reference manual, most of these 5,000 pages of PDF. They implemented manually in a model, and we are going to compare their semantics against our semantics to see if there are any differences. And when we do that, we did find some differences. So we found 32 variants where there was some kind of difference between the semantics from Dasgupta and the automatically generated semantics from libLISA. And we manually looked at all of these semantics, and we classified whether they were an error in the manually written semantics or an error in libLISA semantics. And it turned out that most of the cases, in 28 of these cases, was actually an error in the manually written semantics. But there were also a few cases where libLISA's semantics were incorrect. And that's caused by the synthesis that we used. So the program synthesis that we use forms a hypothesis and then tries to verify this hypothesis by fuzzing. And if it has encountered 2 million cases where this hypothesis seems correct, it will consider the entire hypothesis correct. And as it turns out, 2 million cases is not quite enough to always capture the full behavior of some of these instructions, which is why there were some errors. And this can, of course, then be fixed by either increasing the threshold on the number of cases that you want to observe before you consider your hypothesis valid, or you could fix this by finding your test cases smarter and increasing the quality of the information that you get from each counterexample that you find. So finally, if you're interested in taking a look at these semantics, I would recommend using explore.liblisa.nl. This is a website where you can look at these semantics in a sort of human-friendly way, and you can actually also simulate the execution of these instructions and export it to SMT code if you want to. So in summary, libLISA is a tool that automatically discovers and infers instruction semantics. We analyzed 5 different architectures and found differences in the undefined behavior. And all of these semantics and source code is all available under open source licenses. Thank you for your attention. If there are any questions, I'd be happy to try and answer them.
Go ahead.
Hey, nice talk. Can you hear me?
Yes.
Yep, cool. I guess you can infer you infer the semantics from architectural state, is that right? Can you infer stuff that you wouldn't necessarily observe directly? I'm thinking like microarchitectural things or side channel-like things that require maybe another thread to do some magic to.
So it's not, in this work, we're only looking at the actual architectural state, so we're not doing any of that. But I am aware of some tools that automatically, for example, try to infer the timing of instructions. And that could also be combined with this. So, it depends on what exactly you want to observe. But as long as it's observable, you can do it.
Yeah, I mean, I'm just thinking from a CPU design perspective, a lot of the value is in how they make it fast under the hood. And it might be useful to have the semantics for that as well as the visible stuff. But that's cool, thank you.
Hi, really cool work. Sometimes CPUs ship with bugs, which is okay because you just get your computer to patch the microcode really early on and you're fine. Could you use libLISA with microcode patched or not patched to see, kind of to reverse engineer the bug if the manufacturer doesn't really reveal what it was?
So there are some cases where you can do this, yes. So I believe the w.r.t bug was one that, unfortunately, it was out of scope, the specific instructions that caused it. But if it had been in scope, we would have likely found that bug as well.
Okay, cool. I have one more question. What about hardware transactional memory instructions? Those take a lot of state that lives, in the cache and all of that. So can you work with those?
It's out of scope in this work.
Okay.
I'm not familiar enough with the exact details to be able to tell you if it's possible to analyze those instructions or not.
Okay. I encourage you to take a look. It's super cool.
Thank you.
Thank you.
Did you find any NSA backdoor?
Any what, sorry?
Any NSA backdoor?
No, I did not. Unfortunately not.
The correct answer is neither confirm nor deny.
So I would imagine that if you have some arbitrarily niche or complicated instruction, I don't know, just say we have an instruction that does a matrix multiply, then now your tool that can generate hypotheses about the semantics of that needs to be able to model arbitrarily complex instructions. Like, how does that look? I mean, if I came up with something like a cryptographic instruction that's doing some crazy hash function, are you able to model that? And that seems like a very hard problem in of itself. So can you speak more about that part?
Yes, so yes, in general, it's just a hard problem. But one of the advantages is, so it's hard with program synthesis in general. But one of the advantages with doing it with CPUs is that a lot of these CPU instructions are very simple, right? I believe something like 70% of all encodings that we found are just doing data moves.
Yeah.
So yes, there are some instructions, for example, cryptographic instructions that are hard to synthesize. And in such a case, you might have to add a specific operation that does the operation you want to synthesize to your synthesizer.
Okay, thanks.
Any other audience question? So I have one more. If I understand, so you're inferring these templates, the shapes of the instructions, and I'm wondering how important is it to infer that as opposed to have that one of the things a human provides? Because usually you can see the beginning of the reference manual will say, we use these patterns for instructions.
That's a very good question. So my point would be that, yes, we might see it in the reference manual, but how do we know it's actually implemented that way in the actual CPU? And especially for example, undocumented instructions, how do we know how they are encoded? So I think it's valuable to spend some CPU time on automatically inferring these if it's possible.
Did you compare the inferred templates to the ones in the manual to see whether there were differences? Okay, I would be interested, but that sounds like actual work too, right? Okay, well, let's thank Joost one more time. Thanks.